Hey y'all, so this is going to be the last video I'm going to do for section 7.5, and then I'm just going to post my notes from there on out. So basically this fourth example that it gives you is continued in the fifth example. So the fifth example just kind of goes over what we end up finding, and I'm just going to kind of leave that to you all to see. Even the textbook kind of is like, here on out, it's extra. So I feel okay just posting notes about that. If you have any questions about it, just ask in the comment section below and I can try and answer them. So I'm gonna share my screen and get started with y'all. All right. So the first thing about this, so basically this problem is a bead on a spinning wire hoop. So the hoop is standing up like up vertical and spinning kind of like a coin while the bead is going around the loop, because they really wanted to make it annoying for us. Um, but the point of this, luckily, is to see that it's not that annoying. That's really all this section is showing us. We thought it was annoying. Turns out it's not. So in order to solve this problem, the textbook gives us a few things that we need to know. And for starters, it tells us that the bead's velocity is equal to r times the change of theta. And that points tangent to the hoop, so it kind of goes, that's the velocity going tangent to the hoop. And then so rho, which I have designated right there. So basically the bead's distance from the axis in which the hoop is spinning on. So that times that angular velocity that it's spinning at is going to be equal to r sine theta times, again, that omega angular velocity that's going on. And the thing to know about that is it is going to be normal to the hoop. So just for stating purposes right here, these two equations are perpendicular. Orthogonal. Orthogonal is probably a better term for them. But either way, we're going to remember that. So I'm going to take you down from the hoop and we're going to kind of just start in on the Lagrange equations. So write out Lagrange here. Boom. Cutest little equation you'll ever have to memorize. So we're just going to go ahead and start solving that. So basically we need our kinetic energy, which is going to be 1/2 mv squared. What is v squared? That's going to be both of those. So, that's what this is. It's the change of rho up here. I added a little dot above, just so I get it right. So I'm showing you all the right thing. I would like to start by showing you all the right thing. Times that mass. Both of them are multiplied by r, so I'm going to bring it out, but we're going to note that the velocity squared, so I'm going to bring out r squared. Great. And theta dot squared plus omega squared sine theta. Great. So that's what we need to know. Actually, I'm being a dum-dum, and this is definitely not rho dot. It's just rho times its angular velocity, because angular velocity is going to be the way in which that rho moves. So it had itself worked out, and I shouldn't second guess myself. So bear with me here. It's exactly what I have written down as of now. It'll show up in the notes. All right, so that is it. That is my final answer. Now I'm going to find my potential energy. So mg, take out an r again. So this is just going to be like basically what that is the cosine. This is up and down direction. So it's literally just wherever that beat is in the y direction. That's what it's going to be. It's like, I would like to know only about its gravitational potential in the y direction. Because gravity, this problem is only in the y direction. Good enough. So then what we're going to do is we're going to plug these two black equations into that green equation right there. I'm going to write them down here with a lot of room so we don't have to mess with it. So Lagrange is equal to 1/2 m r squared theta dot squared plus omega squared sine squared theta. All right, that's in that parenthesis, minus mg r 1 minus cosine theta. All right, so that's what we end up with. It's kind of gross looking, and even the textbook was like, gross, let's go. So gross, let's go. Next thing we're going to do is we're going to take the Lagrange with respect to theta, because if you notice, theta is really what's kind of affecting there. So omega, omega, the angular velocity is constant in this problem. So we don't have to care about it. I like it when that happens. We don't have to care. This has 1 degree of freedom, and it is about that theta. So we only have to do 1 Lagrange, and I like that. All right. So that's our cute little Euler-Lagrange equation. And we're just gonna plug and chug, y'all. All right, let's take that derivative with respect to theta. So we're just gonna be left with this part. So negative mg r, but then it's theta inside there. So we're gonna end up with positive. Goodness gracious. Positive sine theta. Bear with me. And then when I forgot a part. Isn't that cute? This first equation also has a theta in it. Funnily enough. Right, so let's take that derivative. When we do that, we end up with a plus 1/2 cancels with the 2 of the exponent. So we get we end up getting m r squared omega squared times sine theta cosine theta. Brilliant. Now let's take the derivative with respect to theta dot, which is a lot cuter and simpler, and I like it much, much more. And we're just gonna kind of like do both steps out at the same time. So we're gonna take its derivative with theta dot, which is gonna be m r squared theta dot, and then we're gonna take its time derivative, which is gonna be m r squared theta dot dot. Pretty simple. Most of the time derivatives end up just being like, throw an extra dot on there and move on. So that's really nice when that happens. For convenience sake, my own mental capacity, I'm going to not have that plus sign in front of it, but we all know how that got there. So now what I'm going to do is I'm going to solve for theta dot dot. So theta dot dot right there is going to be equal to, bear with me. Okay. Whoa. It's going to be equal to omega squared times the cosine theta of minus g over r sine theta. All right, so just real quick explanation, all the m's cancel. I divided by r squared, and then I factored out a sine theta, just for a simplified answer. I'm going to pretend I did that all in my head right now, but actually, I definitely had it written down. So that's what we're looking for there. And then we want to find an equilibrium point. So that's going to be when this theta dot dot is going to be equal to 0. So how we're going to find that is we're going to set it equal to 0 and solve for theta. I'm just going to be right in there. Oh, it went too far. All right, minus g r, now the parentheses. Oh, look, theta again. Okay, so the first thing we're going to do is divide by sine theta, which is going to be 0, and need to cross it out again. So we don't care about that sine theta, not one bit. That's why we like to factor things. So now I'm just going to go with this. So omega squared theta equals g over r. And then I'm just going to divide by that omega squared and do an arc cosine. That we get theta, it's going to be equal to plus or minus arc cosine of g, so gravity, over square root. There, over that. Over omega squared times r. So basically what the textbook Van Gogh's point out is this looks a lot like harmonic motion, and there's like this whole section in harmonic motion about these equilibrium points, and that's what the rest of the chapter kind of balances on. But I can't remember if I've done them or not, but if I haven't yet, I will be doing them soon. The textbook has a chapter on harmonic motion, and there's a whole section about these equilibrium points. So I'm just going to kind of tell you the results here. And if you want to find out how I got those, just watch those videos, or the videos will be up soon. It's chapter 5, I think somewhere around like section 4 or something like that. Basically, at the two equilibrium points we get, if omega squared is going to be less than, so this omega squared here is going to be less than g over r. So that's the relationship we're seeing right here. We're gonna get two equilibrium points, and that's based solely on cosine's sort of boundaries. And then if omega squared is greater than that g over r, there's gonna be more than two equilibrium points. So that's all that I'm going to be going over in this video. If you want to see a little bit more on what makes those equilibrium points interesting, it mainly has to do with them being stable. I'm going to put that in my notes, which I'm giving you a link to down below in the description section. So you can check that out. And then I'm also going to include the textbook's final example, which just goes a little bit more into this. That way you don't have to watch so many videos, and you have a little bit of getting yourself through it and figuring it out yourself. But if you have any questions, just put them in the comment section below, and I'll try to see if I can answer them. All right, bye y'all.